So this is the homework paper that you've been assigned, which is Summer 23, Paper 22. Let's get started. So the first part of this question deals with, again, kinematics, as is usually the case. So 1.1 shows the speed time graph of a car traveling on a straight horizontal road. So it's a speed time graph. So first off, note that this is a speed time graph. Then let's talk about their features. So I know that the area under this graph is going to be distance, right? And the gradient of this graph is going to be the acceleration. So it says describe the motion of the car shown in 1.1. Now obviously I can first see the speed is constant and then it starts to slow down. But also it does not slow down uniformly, right? It's not at the uniform rate, it's not going down in a straight line. Rather, if you see, then you can see that the gradient here is decreasing. So it is slowing down, so it is decelerating, but it's decelerating at a decreasing rate. I would say that this is decreasing deceleration. Why is it decreasing deceleration? Because the gradient is getting less negative. So for the motion of the car, I'll say that it first travels from 0 to 10 seconds. It has a constant speed of 18 meters per second. I hope you guys can see this value. So between 10 and 20 is going to be 15, so 16, 17, 18. And then from 10 to 50 seconds, it travels with decreasing deceleration. All right. On to the next part. At time t equals to 10 seconds, the engine of the car is switched off. So now we understand this is why the car must have started to slow down, because the engine was switched off. The brakes are not applied. So the momentum of the car is taking it forward, but gradually it's slowing down. Now if it's slowing down, this also makes sense that this car is decelerating. And if you think about Newton's laws, so there must be some force which is acting opposite to how this car is moving. That is what is slowing it down. So right now the car is going like this, but for this to decelerate, the acceleration must be in opposite direction to its velocity. So the resultant force by Newton's second law must also be backwards. Now it tells me to name two forces that act on the car to cause the change in motion. So what are these resistive forces which is going to oppose its motion? One of this is obviously the friction between the tires of the car and the road. And the next one is going to be air resistance. The next part then asks us, suggest why 1.1 is a curve. So why is this not a straight line? Why does it not constantly decelerate? And the answer to that has to do with these factors if you think about this. So you know that friction is usually a constant value. That's what you know for now. But air resistance, you know, changes with speed. And as you can see here, the speed was decreasing. So with the speed decreasing, the air resistance would also decrease. So there's a changing resultant force here, which is also causing a changing acceleration. So you know that air resistance decreases with speed. And that's why you can see that the resultant force would also decrease and the acceleration would also decrease, which is exactly what we wrote, right? Here we called it deceleration because obviously it's opposite in direction to how the velocity was. Between 10 and 20 seconds, the speed of the car changes from 18 meters per second to 11 meters per second. Mass of the car is this much. Calculate the change in momentum of the car in this time. So change in momentum, delta P would be final minus initial. And also I know that final momentum is mv, initial momentum is mu. factoring out the m as common, I can also write it as this, m times v minus u. Final speed is 11, initial speed is 18, and also m is 1200 kg. I know this is going to be a decrease in momentum because the speed has decreased, but again the answer just asks me for the change in momentum. So ignoring the negative sign, this is 8400, and units could be either Newton second or kg meter per second. Both are correct answers. Calculate the average resultant force exerted on the car during this time. So you just found out the change in momentum. For the resultant force, you can use the very definition of force, delta P over delta T. So 8400 is delta P, time is 10 seconds from 20 to 10, from 10 to 20. So this would turn out to be 840 newtons. Next question, 2.2 shows a rider on an electric scooter. The scooter contains a battery and a motor to drive the back wheel. State the name of the energy stored in the battery. So we know that this is chemical potential energy, which is stored in batteries and in fuels. Describe in terms of work done the stages of energy transfer from the energy stored in the battery to the kinetic energy of the scooter. So there's this battery which contains chemical potential energy, and you also have to link this here with the concepts that you've studied in electricity. The idea is that this chemical potential energy in the battery will first be converted into electrical energy by this closed circuit that the battery and the motor are connected in. So the chemical potential energy is converted into electrical energy. Now we could have written all of this expression in terms of energy, but the question is explicitly asking me to explain this in terms of work done. So instead I'll say that chemical potential energy is converted to electrical work done by the flow of current, right? And then this electrical work done, when it's applied to the motor, this causes the motor to do work, and that is what drives the back wheel. So this mechanical work, or you can also just say work, by the way, is then done by the motor on the back wheel. Total mass of the scooter and rider is this much. Calculate the total kinetic energy when the scooter has a speed of this much. So again, just the formula. Kinetic energy is half mv square. So half times 70 times the square of 4. So this turns out to be 560 joules. Next question, the battery is marked energy capacity 0.35 kilowatt hour. Define what is meant by a kilowatt hour. Pretty basic stuff. This is the energy. So this is the first thing that you need to get right. It's not the power, it's the energy, because kilowatt is power times time makes it energy. Energy used by a 1 kilowatt appliance or device when used for 1 hour. The next part, the scooter stops working because the battery is totally discharged. This means that there is no more energy stored in the battery. The battery is then recharged using a 70 watt power supply. Calculate the time taken to fully recharge the battery. So the battery has energy given by this formula, E equals PT. So the energy capacity is 0.35 kilowatt hour, right? At this point, I'm not even memorizing these formulas. I'm just looking at the units and then understanding how the formula should work. The power is 70 watts, but let's say that if I also want this to be in kilowatts, I can also write this as 70 over 1000 or 0.07 kilowatts. Or you could have also done this, that you can multiply this 0.35 by 1000 because that's what kilo means, and then I get the time in hours. So 0.35 over 0.07 gives us 5.0 hours. Next question. A fixed mass of gas in a glass tube is trapped by a seal at one end of the tube and by a column of mercury. The mercury is free to move within the tube. The tube is rotated slowly from the vertical as shown in 3.1 to the horizontal as shown in 3.2. The volume of the gas increases and the temperature remains constant. So it says that in going from 3.1 to 3.2, the volume of the gas increases. A part 1 says describe why rotating the tube changes the pressure of the gas in the sealed end. So if the volume of this gas has increased, this means that the pressure must have decreased, right? This is actually what's asked in the next part. A part 1 just asks, describe why rotating the tube changes the pressure of the gas in the sealed end. So the reason, you can see that from this diagram in 3.1, the mercury is directly sitting on top of the gas, whereas here the gas is freer to move, right? So you can see that the mercury, because its weight is not directly acting on the gas anymore, it exerts a reduced pressure. So mercury exerts a reduced pressure since the weight does not act on the gas now, right? So it's no longer sitting on top. All right, next question. Part 2, explain using ideas about particles why the pressure of the gas decreases when its volume increases. Now this is some really important stuff that we studied back in KMM, kinetic model of matter. That's exactly what you have to write here as well. So when the volume increases, you know that particles now occupy a larger space. Remember that gas pressure is exerted because of the collisions of the particles with the walls of the container. So you'll say that now particles collide less frequently with the walls exerting a lower force and hence leading to a reduced pressure. Next part, in 3.1 the length of the mercury column is 0.3 meters, density is given, atmospheric pressure is given, calculate the pressure of the gas in the tube. Now if we look here in 3.1, we have this as the mercury. So we can basically find out the pressure that the mercury exerts here because of this depth, and really that is just the pressure due to the weight of the mercury. But then additionally, there's also going to be the atmospheric pressure acting down on the gas. So both of those pressures would act here, right? And again, if the gas is in this position, if it's not being compressed any further down, this means that the gas is also exerting an equivalent pressure upwards. So first let's find out the liquid pressure, which is rho gh. rho GH, and then rho is 14,000. In the new syllabus, G is 9.8 and H is 0.3 meters. So this is exactly 41,160. You are also given the atmospheric pressure, so you can just add this now. So this turns out to be total pressure with adding the atmospheric pressure is 1.411, or you can say 1.41 into 10 to the 5 pascals, or to 2SF 1.4 into 10 to the 5. Part C, the pressure of a different sample of gas changes at constant temperature. 3.3 shows 1 point marked X on a graph of pressure against volume for the gas sample. At X, the pressure of the gas is P naught, volume is V naught. So we know that at constant temperature, pressure and volume are inversely proportional. So if we have this data point where pressure is P, volume is V, we know that if the volume would double, by the definitions of inverse proportion, the pressure would halve. Similarly, if the volume halves, the pressure would double. So it gives us a graph that we expect like this. Let's go on. .1 shows the particles at one instant in a sample of iron at a temperature below its melting point. State the lowest possible temperature on the Celsius scale and on the Kelvin scale. So we know Kelvin scale, the minimum temperature is 0 Kelvin, which corresponds to -273 degrees Celsius. Temperature of the solid increases, the sample remains a solid. Describe how the motion of the particles change. So very straightforward, you'll just say particles vibrate still, because this is still a solid, further and faster. Some people also like to include wave terminology with this. They say that the particles travel faster and have a greater amplitude of oscillation. That's also fine. Part 3, the solid melts. State what happens to the internal energy and the temperature of the solid as it melts. So temperature stays constant at state changes. But remember that the internal energy is the potential energy plus kinetic energy. The potential energy increases, nothing happens to the kinetic energy because the temperature is constant. But since the spacing increases, potential energy increases, which causes internal energy to increase as well. Part B, a student places a 300 grams piece of iron in boiling water until the iron is at a temperature of 100 degrees Celsius. Student removes the iron from the water and places it immediately into 100 grams of water at 25 degrees Celsius. Iron cools, water warms, as you would expect, to the same temperature, 44 degrees Celsius. SHC of water is given. Look at the units, because you'll need to make sure that the units for mass are consistent with this. No energy is lost to the surroundings. Now there's also been questions of this type in MCQs without any hint whatsoever. But in this one, the examiner is much nicer to you, because he gives you two parts, basically building you to the strength that you can actually find what he wants out. The idea is that when the iron is going to be placed into something of a lower temperature, obviously the iron will cool and the water will warm. But also because of the transfers of energy, the thermal energy lost by the iron would be equal to the thermal energy gained by the water. This is the idea here. First part says calculate the change in internal energy of the water as it warms up. So 100 grams of water as it warms up. So it would gain internal energy. MC delta theta, M is 100, C is 4.2. In delta theta, so it starts out from 25, goes up to 44. 44 minus 25 is 7980 joules. Calculate the specific heat capacity of iron. So the idea is that the energy lost by water, the energy gained by water is equal to the energy lost by iron. So 300 grams of iron, we need to find its we need to find its specific heat capacity. And temperature change for this, it goes down from 100 to 44. Now I obviously know that this thermal energy has been lost by the iron. So I know that the temperature is going to be decreasing. But so that my answer for C comes out to be positive, because I already know that this energy should also be negative, I'll just play around with the signs so that this turns out to be positive. Usually I would do final minus initial, 44 minus 100. But to make this turn out to be positive, I'm going to do 100 minus 44, which is 56. So 7980 over 300 times 56 turns out to be 0.475 joules per gram per degree Celsius. Water waves are transverse waves. Underline two other examples of transverse waves. So seismic S are transverse waves, and similarly X-rays are also transverse waves. Right? This is just stuff that you need to know. Part B, figure 5.1 shows a wooden bar and a glass block in a ripple tank. Depth of water in the tank is less than the height of the glass block. So what this means to say is diffraction cannot take place here, because it's blocking all of the water. It's sticking out of the tank basically, and it's not letting any water pass over it. So it's not creating regions of shallow or deep. The wooden bar moves up and down once every 1.15 seconds to create the crest. Speed of water wave is given. Calculate the frequency and wavelength. So we have the time period, right? The time period of oscillations, which is also going to be the time period of the waves. And simply by using this relationship, I can figure out the frequency. So 1 over 0.15 is what we need to do. So 6.667 or 6.7 hertz, and lambda, so we can use V equals to F lambda. So lambda is V over F. So 27 centimeters per second divided by this thing turns out to be 4.05. Again, if you use the exact calculator value, that's what you get. If you use this value, then you might get a rounding error. The wave diffracts at the right hand edge of the glass block. On 5.1, draw two crests after they pass the glass block to show the diffraction. So we have to draw two crests. Remember that the diffraction causes them to bend. Also remember that diffraction does not have any effect on the wavelength. So approximately how much this distance is should also be how this much of this distance is. Again, as stated previously, if you feel like your diagram is not reflecting this very clearly, just label it explicitly. The next part asks, describe how a wave with a smaller wavelength is made with the wooden bar. So remember that as long as we stay in one medium, the speed of the wave is going to be constant. So if I need a smaller wavelength, I'll need to increase the frequency. And here, if you can see, the movement of the wooden bar was what was creating the waves. So you will say that increase the frequency of movement of the wooden bar. Describe how a decrease in wavelength affects the diffraction. Whatever happens to the wavelength will also happen to the diffraction. So it causes a decrease in bending or a decrease in diffraction. Next question. 6.1 shows an electric circuit containing a filament lamp, a resistor R, a 12-volt battery, and 5 meters. So this, as you can see in the diagram, comprises both the ammeters and the voltmeters. Reading on ammeter A1 is 0.25 amperes. So if I look at this diagram, all the ammeters are in series. So the reading on this is also what the reading would be shown on all the ammeters, because that's the current flowing through this loop. Reading on the voltmeter V1 is 3 volts. So out of this 12 volt, 3 volt falls across this resistor. It also makes sense that if I apply the voltage division argument, the rest of the 9 volts must have fallen across the resistor R. Determine the readings on the other meters. So as we just discussed, ammeter A2 would also show 0.25 amperes. A3 would also show 0.25 amperes. And V2 would show 9 volts. Again, units are already given. This is a new start in O levels. So let's get rid of this here. Otherwise, it would just be redundant. Resistance of resistor R. So for resistor R, I know the voltage across it. And again, because this is one path, I also know the current through this. So for the resistance, I just need to do V over I. So R equals V over I. So 9.0 over 0.25 turns out to be 36 ohms. Again, units are given. The resistor obeys Ohm's law. State Ohm's law. Remember that you need to say this thing, otherwise Ohm's law is not going to hold. And you will also lose a mark. You need to say that for constant temperature, then you need to quote the direct proportionality. So voltage across component is proportional to current flowing through it. Next one, part B. 6.2 shows the current voltage graph for the filament lamp. As we expect, since the resistance increases, remember that the voltage curves towards, the graph curves towards the voltage axis. Because for the resistance to increase, if I just write out the formula here, the voltage must increase faster than the current. So this is replaced, the battery in 6.1 is replaced with a different battery which has a different EMF. Voltage across the lamp increases to 6 volts. Use data from the graph to determine the EMF of the second battery. Show your working. So first off, let's see that what does the 6 volt reading correspond to on the graph. So 6 volts very clearly corresponds to the 0.35 amperes reading. Right, so this current is very clearly 0.35 amperes. Now let's go back to the graph, because this is now a different voltage source. So for the filament lamp, this is the 0.35 which goes through this. And as we discussed, that's also the current which is going to be flowing through this. Now we just found out the resistance, right? And we can also very easily find out the resistance of the filament lamp. And if we also know the current, then I can very easily also find out the EMF. So when I do this now, the resistance of the lamp is 6 volts over 0.35 amperes, which is going to be 17.14 ohms. And the resistance of the resistor, actually, this was 36 ohms. So the total resistance would be the sum of both of these. So this plus this turns out to be 53.14 ohms. I also know the current flowing through both of these, which was 0.35 amperes. So the EMF would be IR, the current times the total resistance. So 0.35 times this thing. Again, if you use exact values like me, you'll get the exact answer, 18.6 volts. Let's go on to another question. Next question, UV radiation is one component of the EM spectrum. State the name of two components of the EM spectrum that have a smaller wavelength then ultraviolet. So smaller wavelength can also be interpreted as higher frequency. So after UV, if you remember the mnemonic, raging Martians invaded Venus using X-ray guns. So it's X-rays and guns is gamma rays. Gamma rays. State one useful application of UV radiation. So it's used in security marking, detecting counterfeit bills, and tanning, right? All of those, sterilizing. Exposure to UV radiation from the sun damages the eyes. This is because of the ionizing effect of UV radiation. State one type of damage to the eye caused by UV radiation. Very straightforward. Cataracts in the eye. So this shows a ray of light. Ray passes into a semicircular block at A and leaves the glass at B, traveling along the surface to C. So as you can see, this is forming the critical angle case. State the name given to the angle of incidence marked as 40. This is the critical angle. Calculate the refractive index of the glass. So we know this relationship, n equals 1 over sine C, or sine C equals 1 over n. So when we use this, so we do 1 over sine 40. So correct to 2SF, this turns out to be 1.6. 8.1 shows a step down transformer. As you can also visually guess that these secondary turns are less than the primary turns. This also means that the secondary voltage would be less than the primary one. So this is a step down transformer. State the material used for the core. Very obvious. Iron or soft iron, whatever you want to say. A current in the primary coil produces a magnetic field in the core. Explain how an alternating voltage is produced in the secondary coil. So how is that alternating voltage produced? First of all, remember, even though it's not marked here, the input voltage is also alternating. So the alternating input voltage or you can also say current, this leads to a changing magnetic flux. And because of this changing magnetic flux, you can say that field lines are cut by the secondary coil. Inducing a alternating EMF. Again, this is just a question that has been asked a lot in recent years, but it also used to be asked before that. Primary has this many turns, is connected to a supply of this much, output of this much is needed. Calculate the number of turns needed on the secondary coil. So NP over NS equals VP over VS. I need NS, so I can, again, it's just my choice. I'm doing this first in symbols. So NPVS over VP. So NP is 4600, VS is 5, and VP is what? 230, right? So this gives me exactly 100 turns is the answer. State one change that can be made to the transformer in 8.1 so that it can be used as a step-up transformer. So it's just one change. So you just change the input and outputs, right? So reverse the coils so that input becomes output. and vice versa. 9. A radioactive source emits alpha, beta, and gamma. State which type of radiation produces the strongest ionizing effect. We know because of its high charge, it's alpha. Right? High charge and low kinetic energy allows for a lot of ionic interaction. State which type of radiation is deflected most by a magnetic field. The answer is beta, because even though alpha has a larger charge, beta has a much smaller mass, which causes it to be deflected more. 9.1 shows a GM tube and a counter. A radioactive source is placed 10 cm from the GM tube. In figure 9.2, a piece of metal 5 mm thick is placed between the source and the GM tube. The readings on the counter have been corrected for background radiation and show the current rate due to the source. So, with the metal placed, which you know blocks beta, the count rate falls to 600. Falls by 600, so from 800 to 200. So explain how the readings show that the source emits beta as well as gamma. So you know that with the metal, the count rate drops by 600 because this is beta being blocked. But after this even, 200 is still detected. Because gamma can penetrate the metal. Next one, state why the readings cannot be used to show that the source emits alpha particles, because the metal plate which blocks beta would also block gamma. But another thing is that the range of alpha particles in air is much less than 10 centimeters. So they would get annihilated in the air, right? So alpha is stopped by a few cm of air. Describe one way that a radioactive source is moved safely in a school lab. So the answer to this could be, there could be multiple answers. I'll say use of forceps to handle source. Last question. Astronomical distances are measured in light years. State what is meant by a light year. So distance traveled by light in a year. The sun is one star in the Milky Way. State the approximate diameter of the Milky Way galaxy. It's just a value you're supposed to know. 100,000 light years. There are several stages in the life cycle of a star. Complete 10.1 to show the stages that a massive star goes through after it has used up most of the hydrogen at the center of the star. So a massive star turns into a red supergiant and then it explodes in a supernova. After the supernova, again you have a nebula which is formed, and that eventually leads to a black hole as the nebula is later expelled. Or in the case of a star which is not as big, it may also lead to a neutron star. State the stage in the life cycle of a star where heavy elements are formed. Obviously this is during the supernova stage, right? This is when carbon fuses to form iron. Current scientific understanding is that the universe began 14 billion years ago in an event known as the Big Bang. Explain one observation that supports the Big Bang theory. So the observation is redshift, obviously. And you know redshift is the increase in the observed wavelength, or you can also say the decrease in the frequency of the light received by distant galaxies or stars. And the reasoning behind this is that if the wavelength is larger, this means that the galaxies or stars are receding away from us. Also, we know that light from more distant galaxies is more redshifted. Right, so that shows a greater decrease in wavelength, a greater increase in wavelength from galaxies further away are more redshifted. So if they're moving apart now, so since the universe is expanding, universe is expanding, the stars and galaxies should have been together at the start. Right, so that's the answer to this one. So that sums up this paper. See you in the next one.